I'm going to discuss the problem of the vibrating molecule and how we can treat it classically. And the molecule is going to be a diatomic molecule. So the diatomic molecule we will think of as consisting of two nuclei. There's one nucleus, there's the other nucleus. We'll say one is bigger than the other. And then surrounded by a cloud of electrons. There's my cloud of electrons that tends to hold the molecule together. The electrons will tend to pull the nuclei close to each other, and at the same time the nuclei are going to repel each other. And at some particular distance, these balance out and we have a stable molecule. That distance is the bond length, which we're going to call Re. However, the molecule is not, as you may know, rigid, but it can vibrate. R can change. It can be higher or lower, and the molecule can vibrate about this equilibrium distance. So R sub E is going to be the normal bond length, and then R will be a general symbol for the distance between the nuclei. So R will change as the molecule vibrates. So this is basically a one-dimensional problem. The one with the one variable being R. At this point, we should point out that the problem is not quite as simple as this, simply because both atoms move in a vibration. They vibrate around their common center of mass. So if, say, in a vibration, if this atom moves that distance, the lighter atom will move a considerably larger distance in such a way that the center of mass, we'll indicate that by an X here, that center of mass remains unchanged. So there's really two atoms vibrating. However, you can show that this problem can be thought of as equivalent to the problem of one particle one particle moving in one dimension, provided that instead of the mass, the ordinary mass, we use something called the reduced mass, which we're going to call mu. Mu is the product of the two masses divided by the sum. I will just assert that, and I will maybe present to you a little more justification of that, but for now just accept this, that we can treat this as one particle with this mass. The equations of classical mechanics that we introduced earlier, so first of all, we're going to have the potential energy, the molecule is going to be characterized by a particular potential energy function, which we called V, and that's a function of R. I'll show you in a minute what that looks like. The momentum, remember we use, the momentum is, as usual, mass times velocity, but instead of mass we use reduced mass, and for velocity, dr dt. And the equation of motion that we were going to use is dv dr is minus dv dr. That's the force. So remember, the force is the negative of the slope of the potential energy function equals dp dp dt. Okay, so now we'll look at a typical potential energy function for a diatomic molecule. Here's the potential energy function for the HCl molecule. A little bit of interpretation of this. So first of all, we see that as we push the nuclei together and have R go to 0, we see that the potential energy function goes to infinity. This represents the repulsion between the two nuclei. There's a limit to how close they can get. And then as we pull the atoms apart, the potential energy function eventually levels off to a constant value right there, and and out at infinity that represents separated atoms. In the middle region, we can have a stable molecule. The distance at which the potential energy function is a minimum, indicated here, that's R sub E. And that's the equilibrium distance, the point at which the forces balance out. We're also characterize the bond like this by a bond energy, which is simply how much energy it takes to go from the stable molecule at R sub E to separated atoms. And that is on the diagram, that's this distance. So that's the bond energy. On this graph, the y-axis is in electron volts. The x-axis is the distance in nanometers. To illustrate some more about this, I will get a fresh copy of the potential energy function. Okay, so here it is. Imagine we start at the point indicated by the box in the diagram, and we start with the molecule not moving. At that point, there will be a force in the direction of that will cause the bond to stretch. So that force will be in that direction, and the force is, as you know, proportional to the slope of the potential energy function. As the molecule, with our focus on energy, we remember that as the molecule vibrates, the energy remains constant. So as it vibrates, what's going to happen is that potential energy is going to be converted into kinetic energy. It's going to reach a point on the opposite side at an elongated length over here, and at that point the bond in the vibration, it will turn around and go back, and it will continue going back and forth between these 2 points, and those are the so-called turning points. Okay, in the course of its vibration at any particular distance, we'll say this distance here, the total energy is constant. The potential energy is this distance here, V, and the kinetic energy is the distance from here to here. So that that distance that I've just indicated, that is T, kinetic energy. So as the molecule vibrates, potential energy is converted into kinetic energy, and then it has maximum kinetic energy at the equilibrium distance, and then it starts slowing down until it gets to the other turning point as kinetic energy is converted back into potential energy, and then it turns around and goes back. So basically, this just concludes my presentation of the qualitative nature of molecular vibration, and we are going to do some mathematics with the harmonic oscillator, but this is just the qualitative picture. A couple of things that I want you to do here. First of all is kind of an exercise in dealing with units, and that is, I want you to look at this HCl system and calculate the reduced mass in SI units. So remember that basically here we have the expression for reduced mass, M1, M2 over M1 plus M2. And to do the reduced mass, a couple of things that we should note. If you look up masses in the periodic table, you should realize that those are not masses of individual nuclei. They're average masses of isotopes. And chlorine has actually 2 common isotopes. So in the periodic table, you'll see a number something like 35.5. But that's actually the average of isotopes of mass 35 and mass 37. So for our purposes, we won't use real exact masses, but we'll say M1 will be that of hydrogen, and that will be 1 atomic mass unit. And then M2, well, we have 2 common isotopes of chlorine, and we will use the lighter one, 35 atomic mass units. Okay. Later we can do this by using very accurate, very precisely known isotope masses, but we'll just use these. Okay. Now, the units of this, I could use this to calculate the reduced mass. The units will be atomic mass units. Well, what is an atomic mass unit? 1 atomic mass unit is 1 gram per mole. So when I get this reduced mass in atomic mass units, it's not in SI units. The SI units are kilograms, but not per mole. So I have to do 2 conversions to get this into proper SI units of kilograms. So first I have to do grams to kilograms, and then I have to divide by Avogadro's number. You learned this back in kindergarten. Approximately 6 times 10 to the 23rd. Okay? And then I'll have the reduced mass in atomic mass units. Okay, so that's one problem I want you to do. Next, the other problem I want you to do is to, again, qualitatively look at this and try to imagine what a graph of the internuclear distance, the R, as a function of time would look like. Starting with, as shown on the diagram, a molecule has a total energy starting at 2 electron volts. So as I'm starting, then on this axis is going to be R, and on this axis is going to be time. And then I can see I start at a distance of 0.1 nanometers, and we'll say do 0.1 here, because you see that's what that's where the total end. That's the point at which at 2 electron volts, that's the minimum distance, as you can see from the diagram. That's where I had the box on the potential energy curve. Now, as the molecule, at that point, it starts out with 0 velocity, and then it, because it's feeling a force pulling it apart, R is going to increase. Okay, and it's going to reach a maximum velocity when it gets to the equilibrium bond length, and then it's going to start slowing down and turning around, and it's to a point where it's going to start turning around. And I'll just let you complete the diagram. What happens to R as a function of time? And looking at the diagram, I can see where it gets to about 0.2 electron volts. At that point, as I said, it stops. That's the other turning point. It stops and turns around and comes back. So just complete the diagram. Then the other problem I want you to do is to, again, considering the same thing, look at what you think the kinetic and potential energy should be doing as a function of time. So you can put these on the same plot. That'll be my energy scale, energy, and this will be time. Okay, now qualitatively, what do you think is going to happen? Well, I can see, so for kinetic energy, I'm going to start out at 0 because I started at rest at 2 electron volts. I started at rest and now it's going to rise, and then as time goes on, it's going to then reach a maximum at some point, and it's going to come back down as it reaches the other classical turning point and continue like this. And this would be a graph of T, the kinetic energy as a function of time, and it would continue like this. And then you complete this sketch, and what is V as a function of time? Again, just qualitatively. On either of these plots, we don't have to be concerned about quantitative results, and we don't have to be concerned about the time it takes to go from one side to the other. That will be in when we look at the harmonic oscillator problem. Okay, so this completes the qualitative discussion of the diatomic molecule, and then I will include in the next part of the presentation the harmonic oscillator model for describing